So last time we were looking at this elasticity tensor, and we showed that C is equal to d of tau hat of y is equal to d of t hat of y is equal to d of s hat of y. And so today we will look at some of the properties of this elasticity tensor. So the first property, so the first property is that C of u belongs to sim for all u belonging to min, and the second property is that C of w is equal to 0 for all w belonging to so these are the two properties. The first one actually just follows from the definition itself. So C of u, this is the first property, that C of u is equal to d by d alpha of tau hat of I plus alpha u. So this is just from the definition of the directional derivative. This is evaluated at alpha equal to 0. And since tau hat is a symmetric tensor, so from that we will get that C of u is a symmetric tensor. So since tau hat belongs to sim, we will get that C of u belongs to sim. Yes, and then to prove the second property, we will use material frame indifference. Okay, so this we have that S hat of F is equal to S hat of E. This we have already seen this particular relation. So this follows from material frame indifference, if you recall. And then now we can write this as D of S hat of I is equal to in the direction U is equal to d of s evaluated at 0, d of e in the direction u. So this is, we are just using the chain rule here, and if f is equal to identity, then e is equal to 0. So that is why this we are evaluating it at e equal to 0 here, and then the direction is the directional derivative of E in the direction of U. And then this is equal to half of B of S of 0 times U plus U transpose. Okay, so that so if you now substitute U is equal to W, then U transpose is equal to W transpose is equal to minus W, and then that is just equal to 0. So you get that ds hat of I in the direction u is equal to 0. So that's sorry, in the direction of w is equal to 0. So that shows that c in the direction of w is equal to 0. So this implies that c times w is equal to 0. So one can also give an alternative proof for this particular thing. So alternative proof. So choose W belonging to skew, and let Q of T be equal to E to the WT. So we have seen that this exponential tensor belongs to R plus. So this belongs to R plus. And if you now differentiate, so differentiate tau hat of QF is equal to Q times tau hat of F times Q plus. So this is also material frame indifference, right? So basically the whole proof of this particular result that relies on material frame indifference. So without material difference, we cannot prove this particular result here. So if you differentiate this with respect to time, then what you will get is that d of tau hat qf in the direction of q dot f plus q f dot is equal to q dot times tau hat of f times q transpose plus q times d of tau hat of f times q transpose plus q times tau hat of f times q dot transpose. So just differentiate each term there, and then okay, here this one modification here, d of tau hat of f in the direction of f dot times q transpose. Okay, so that's so the direction also has to be there. So this is f dot. Okay, then let us write it here. Yes. So now if I simplify this particular expression, then what I will get is that q of 0 now is equal to identity, and q dot of 0 is equal to w. Right? So if you evaluate this tensor at t equal to 0, then e to the 0 is identity, and q dot is w times e to the wt. So that is equal to going to be w at time t equal to 0. So this is what you get, and then so you get that d of tau hat evaluated at f in the direction of wf plus f dot. And so basically I am now substituting q dot is equal to w and q is equal to identity in this result. So that's what I will get. So this is equal to w times tau hat of f plus d of tau hat of f in the direction of f dot plus minus of tau hat of f times w. So this is what you will get, and now use the linearity of the directional derivative. So this can be written as d of tau hat of f in the direction of wf plus d of tau hat of f in the direction of f dot. And this term is the same as this particular term, so they will cancel on both sides, and then what you will get is that d of tau hat of f in the direction of wf is equal to w times tau hat of f minus tau hat of f times w. And now we know that tau hat of I is equal to 0. So now put f is equal to identity, and then this will become the c in the direction of w. So that is equal to so this part will become 0 because tau hat of identity is equal to 0, and again this part will also become 0 because tau hat of identity is 0. So you will finally get 0. So c of w is equal to 0. So that we have shown this particular result now. So let us move ahead. Okay, so if I now write u as equal to u symmetric plus u skew symmetric, where the symmetric part is half of u plus u transpose and u skew symmetric is half of u minus u transpose, right? So because of this particular result, c times u is equal to c of us plus uss, which is equal to c of us plus c in the direction of uss, and this is equal to 0 because for the skew symmetric part we have shown that this is 0 for all W belonging to skew. So because of that part will be 0, and hence C of U, C in the direction of U is equal to C in the direction of U of SC. So basically, the C is completely determined by the restriction of U to its symmetric part. So the skew symmetric part of U does not play any role in this one. And so we can always take this direction as a symmetric tensor, because the skew symmetric part doesn't play any role at all. Okay, now let us look at some of the invariance properties of this C, the constitutive tensor here, C. So we have the following theorem now. So theorem: if tau hat is isotropic at frame indifferent and X, then C is invariant under orthogonal transformations. Under orthogonal Q of C in the direction of U times Q transpose is C of Q transpose for all Q belonging to all X. Okay, so let us prove this theorem here. So if tau 1 is isotropic and frame indifferent, and there exists an isotropic mapping tau 1 such that hat of F is tau 1 of F transpose. So this is again a consequence of material frame indifference. So we have already proved this particular result here. So this should be tau 1 here. So there exists a function tau 1 such that tau hat of F is equal to tau 1 of F transpose. So this is for an isotropic and frame indifferent constitutive relationship. So if I now use the definition of this constitutive tensor, so D of tau hat of I is equal to 2 times D of tau 1 of I. Okay. So again here I just use the chain rule here. So basically D of tau hat in the direction of F dot will be equal to D of tau 1 of evaluated identity in the direction of D of FF transpose in the direction of F dot. Okay, so if you evaluate that, you will get that D of tau hat of I is equal to 2 times D of tau 1 of identity here. And so you can write C as equal to 2 times D of tau 1 of identity. Okay, and then now you can write that Q times C of U in the direction of Q times C in the direction U times Q transpose is equal to 2 times Q times D of tau 1 of I in the direction u times q transpose. So I'm just substituting C of u is equal to 2 times d of tau bar, and then this is equal to 2 times d of tau bar of q transpose in the direction of q transpose. So here, this particular step is using the theorem that we proved when we were doing tensor analysis. So we had shown the invariance properties of the directional derivative for an isotropic function, and so we are simply using that particular result here. So for this particular result, go back to the result that we proved in chapter 1 here. And then this is equal to, now simplify this particular expression. So you will get that 2 times tau bar of identity times q transpose, and then this is equal to C of q transpose. And so that proves this particular result, that 2 times C in the direction of u times q transpose is C in the direction of q transpose here. Fine. Now, let us look at the constitutive matrix for an isotropic material. So for an isotropic material, C is a linear isotropic function. Okay, so because linear, because it's a directional derivative, and so it's linear in the direction part, right? And so that is the reason that it's a linear isotropic function. And we also know that C of u belongs to sim. Okay, so using these two properties, we can write that C of epsilon is equal to lambda of x times trace of epsilon times identity plus 2 mu of x times epsilon for all epsilon belonging to sim. All epsilon belonging to C. So that is because this is the characterization for a linear isotropic tensor valued function. And so we are just simply using that characterization here to write the constitutive relation for a linear for a material that is isotropic at x. In initial notation, we can write this as follows. So if I write this in CIJKL form, CIJKL is equal to lambda of x times delta ij delta KL plus mu of x times delta ik delta JL plus delta IL delta JK. So this is exactly, whatever you learn in linear elasticity, that for an isotropic material, the CIJKL is given by this particular form, right? So you have already seen this result in the context of linear elasticity, but we have just proved this result in a rigorous manner here. And now let us define what we mean by C is symmetric. Now, so C is symmetric if A matrix in the product C in the direction of B is B C in the direction of A for all AB. For all AB belonging to length. And if you write this particular property in initial notation, this is Cijkl is Cklij. So this is just the major, what is called as a major symmetry of C here. And then we also define what we mean by positive definiteness. So see, we have already seen that C of W is equal to 0, right, for all W belonging to skew. And so we need to restrict the set on which it operates to the set of symmetric tensors, because anything operating on skew symmetric tensors is just 0. So so that is the reason that we will, when we are defining positive definiteness, we will restrict this set to the set of symmetric tensors here. So so we call C as positive definite, as positive definite. If S times C of S is greater than 0 for all S belonging to sim minus the 0. So I mean all S, so of course S should be non-zero, and then it will be strictly greater than 0. So basically you will have greater than or equal to 0 if and only if S belongs to sim, and it is equal to 0 if and only if S is equal to 0. Okay, so that's what we have here. Fine. Then now let us look at what are the restrictions that lambda and mu are subject to if we impose positive definiteness for this isotropic material here. Let us look at that now. So here assume that the material is isotropic at X, okay, then C is belongs to sim. So that means that Cijkl is equal to Cklij. That's what we mean by the sim. And moreover, C is positive definite if mu is greater than 0 and 3 lambda plus 2 mu is greater than 0. So let us prove this particular theorem. So proof. So let AS be equal to A plus A transpose by 2. BS is equal to B plus B transpose by 2. So these are just the symmetric parts of A and B now. And A times C of B is equal to AS matrix inner product C of BS. So that is because, see, we have seen that C acting on the skew symmetric tensor is equal to 0. So you first split B as BS symmetric plus skew symmetric, and then it will be restricted only to this. And in addition, C times BS is also a symmetric tensor. So that is why you will get A or AS of there, because the skew symmetric part matrix inner product with a symmetric tensor is equal to 0. So you get a S here and an S here because of these properties of C. And then now you substitute. So we know that this is going to be lambda times a trace of epsilon of BS plus 2 mu times epsilon of BS. So let us just write that here. So you will get that lambda times trace of A of S times trace of B of S plus 2 mu times AS BS. So that just using the fact that C acting on epsilon is equal to lambda trace of epsilon times identity plus 2 mu epsilon. So in place of epsilon, now you substitute B of S, and then you will get this particular expression here. And then you will see that this is also equal to BS times C of AS. And this again reversing the steps, just like we got from this step to this step. Now you will get that this is equal to B times C times C. That's how. So that shows that C is symmetrical. Then we want to show that if C is positive definite, then mu is greater than 0 and T lambda plus 2 mu greater than 0. And conversely, if mu greater than 0 and T lambda plus 2 mu is greater than 0, then C is positive definite. So let us look at first the condition for positive definiteness. So if C is positive definite, then S times C in the direction of S is lambda trace of S square plus 2 mu times S is greater than 0. So this is the condition for positive definiteness here. For all S, so this is greater than 0 for all S belonging to sim minus the 0 tensor here. And so choose now S is equal to identity. So choose S is equal to identity, and S belonging to sim such that trace of S is equal to 0. Okay, so choose these things. So then we will get that mu greater than 0 and 3 lambda plus 2 mu greater than 0 here, right? So this will now imply. So if you choose first you choose this, that trace of S, choose a symmetric tensor such that trace of S is equal to 0. This part will go to 0, and then you get 2 mu. This part is always going to be positive, so mu has to be greater than 0. And then once you substitute S is equal to identity, then you will also get 3 lambda plus 2 mu greater than 0. So this will imply that mu greater than 0 and 3 lambda plus 2 mu is greater than 0. Fine. Now we want to show the converse of this particular statement here. And so to show the converse, this one here. So converse now. Converse that choose S belonging to sim and let alpha be equal to trace of S divided by 3 and S naught is equal to S minus alpha times identity. Then you will get that trace of S naught, so this is trace of S naught is equal to 0. Okay, and so you will get that S times C times S is equal to 3 times alpha square times 3 lambda plus 2 mu and plus 2 mu times S naught times S naught. Okay. So if you substitute this S is equal to S naught plus alpha times identity, then this is the expression that you will get. And now from this expression you can see that because alpha square is always going to be positive, 3 lambda plus 2 mu is always going to be positive, mu is going to be positive, and S naught matrix inner product S naught is also going to be positive. So this whole thing is going to be greater than 0 here, right? So that shows that C is positive definite here. Fine. So that proves this particular theorem. So we move to the next property now. So So if we say, assuming that the material is hyperelastic, the material to be hyperelastic, then C is symmetric. So that you can show just simply using initial notation, that we know that T hat is equal to del T hat ij is del W hat by del Fij, correct? And so C ij KL will be equal to del square W hat by del Fij del Fkl. Right? So that is just because it is CIGKL is simply del T hat ij by del Fkl. So you will get this, and then now you can see that this is a symmetry in ij and kl. Right? So this is equal to C K L I G. So just using initial notation, one can show this particular thing here. Okay, so this completes the properties of C I J K L. As I said that this is going to be of use to us when we derive the equations of linear elasticity. Okay, and so if you recall, we are going to consider only very small perturbations about the reference configuration. Okay, and so if you recall, we have evaluated this at F equal to identity, right? It's the derivative of tau hat evaluated at identity, that means F equal to identity. So because that is just the first order term in the expansion for tau hat of F, correct? So that is the reason that this will be useful only when we are deriving the linear elasticity approximation. Okay, so the general CIJKL, which is del T hat by del Fkl, just for any arbitrary F, that actually appears in the finite element implementations. All these fourth order tensors will appear in the finite element implementations when you try to construct the tangent stiffness matrix. Okay, but we are not going to look at that. So we are just going to look at this linearized version at a later stage. So now let me talk about the non-uniqueness of solutions in nonlinear elasticity here. Okay, so non-uniqueness of solutions. So if you recall that in linear elasticity, we showed that the solution is unique, right? And so if you give me a boundary value problem, then just have to find one solution, and then you are done, because that is the only solution. But in nonlinear elasticity, we have non-uniqueness of solution. So let me give you some examples of the non-uniqueness of solutions here. So suppose if you take a tennis ball, okay, and then now you cut it above the equator. Okay, so this is the equatorial line. So if you must have seen this, that your rubber ball that you're playing cricket with, that gets broken, right? Then you take the upper part, which is the smaller part, suppose, and you turn it inside out. Okay, so what is known as eversion. Then actually it will snap back to its original position. But if you take the lower part here, this one, and now if you invert it, that means you turn it inside out, then it will stay in that manner, right? And so that is a example of a non-unique solution. So that the inverted state is another solution, because the tractions on the surface are zero in both cases, right? And then the state of stress in the inverted ball is different than that in the original one. So you can see that the state of stress is different if you take a blade and you cut it here. So that is at the the south pole. Let us say if you just cut it there, then you will see that the lips of the cut, they will separate in the inverted state. but in the non-everted state, that is the original state, they will stay together. So that shows that the state of stress in these two cases is different. Okay, so this is an example of non-uniqueness. So another example is the eversion of a cylindrical tube. So that is like again, if you take your cricket bat, then the rubber that sits on the rubber tube that sits on the handle of your cricket bat, right? If you invert that, that means again turn it inside out, then that is another solution to the equations of elasticity, because you know, the traction again on both these structures is 0, right? And so in one case you will get, so suppose this is the cylindrical tube, okay, then after everting you will see that the ends will flare out like this. Okay, so this so these ends will flare out like this. So that shows that actually this is a different solution than the other one. The everted state is different than the other one, and this is another example of non-uniqueness. Of course, the most famous example of non-uniqueness is buckling. So if you take now a plate, correct, and then try to load it in its own plane, then you know, below a certain critical load, the plate will stay horizontal. But beyond a certain critical load, you know that this plate will either go this way. Right? So suppose this is the original configuration of the plate, and then you are applying loads in this particular direction, it will either go this way or this way, right? And so that is an example of buckling, and so that is also an example of non-uniqueness of the solution here. I mean, so one can cook up a variety of examples of non-uniqueness. So here I have discussed only the traction type boundary conditions, but you can have non-uniqueness for displacement type boundary conditions. So even for a pure prescribed displacement boundary value problem, you can have examples of non-uniqueness, and they are listed in the book here. So basically, you know, so you can see that in contrast to linear elasticity, we have all these examples of non-uniqueness. And so actually, you know, even if we did not know that the material model is nonlinear, from these examples of non-uniqueness itself, we can figure out that the equations are nonlinear, right? So this is so basically non-uniqueness, uniqueness implies that the equations are nonlinear. Because if the equations are linear, then you will get uniqueness, right? And so this implies, but the converse implication is of course not true. So if the equations are nonlinear, we cannot always say that the solution is non-unique. So just, I mean, if you have just a curve like this, a nonlinear curve, right, then you can see that here everything is unique, right? Just for every state here, you have one state here. So it depends on the type of non-linearity. So, but at least from the non-uniqueness, you can definitely say that the equations are nonlinear. Suppose if we did not know that the equations were nonlinear, I mean, we already know that they are nonlinear, but if we did not know that, then we could have deduced that the equations are nonlinear here. So from the non-uniqueness of the solution. So so you can see that actually all the examples of the non-uniqueness of solutions, they involve very large deformations, right? And so that is the reason that in linear elasticity we are restricting the deformation to very small deformations, and there you get uniqueness. But once you allow for very large deformations, then you can get all these examples of non-uniqueness in the solutions here. I think that sort of brings us to the end of this particular chapter. So now we will look at solutions, okay, to the nonlinear equations of elasticity. So now these are sort of exact solutions. So in contrast to linear elasticity, actually finding the solutions in the case of nonlinear elasticity is very, very difficult. Okay. First of all, we have to assume some particular material model, and even if we assume a particular model, because of the nonlinear strain displacement relation, it is extremely hard to find two-dimensional solutions. solution. So most of the analytical solutions in the literature, they are simply like one-dimensional. One-dimensional in the sense that you only have a dependence on one spatial variable, just let's say just x or r, where r is the radial direction and so on. So most of the solutions are not very complicated in that particular respect here, at least for nonlinear elasticity. But at least to get some sense of these solutions, now let us start taking a look at some of the solutions here. Okay, so so let us look at some of the solutions now. So the first example, we look at compressible isotropic. Isotropic. So we will look at Savina first, Savina material. So let us look at some solutions for that. So just a very simple example we'll take, that is a bar that is subjected to unidirectional tractions in this particular direction. So this is just T bar. Let's take this direction as E3 and then the transverse directions E1 and E2. And first, let us just take this uniaxial stretch, whatever. This example here. Because the tractions on the ends are uniform, it is very easy to guess the deformation field, right, in this particular case here. So you can write this as x1 is equal to lambda 1 times x1, x2 is equal to lambda 2 times x2, and x3 is equal to lambda 3 times x3. So you can easily guess what the deformation field looks like here. And you'll get that f is equal to diagonal of lambda 1, lambda 2, lambda 3, and your b will be equal to ff transpose, that is equal to diagonal. By diagonal I mean it's a diagonal matrix. So this is equal to lambda 1 square, lambda 2 square, lambda 3 square. So this is your B. And we can convert, right, from the, so we have the constitutive relation, lambda trace of E times the identity plus 2 mu E, right? So from this you can find out what is the constitutive relation in terms of the Cauchy stress, right? And that will be in terms of B itself. So you will get that tau 11. So tau 11 will be equal to. Let me just see once again. So. Okay, so actually in the beginning we will just not use the constitutive relation for a Savina of material. So in the beginning we will just find a solution for a general material, general isotropic material. So we have seen that this is beta 0 of invariance of B times identity plus beta 1 of invariance of B times B plus beta 2 of invariance of B times B square. So in the beginning, let us just find a solution for this particular case here. So what you will get is that from this particular relation here, you will get that tau 11 is equal to beta naught plus beta 1 lambda 1 square plus beta 2 times lambda 1 raised to 4. And similar relations for tau 22 and tau 33. So let us write that. So we will get that tau 22 is equal to tau 22 is equal to beta naught plus beta 1 lambda 2 square plus beta 2 times lambda 2 to the 4, and now T3 is equal to beta naught plus beta 1 lambda 2 square, lambda 3 square plus beta 2 times lambda 3 raised to 4. And the traction boundary conditions are that you'll get tau 1 is equal to t bar, right? And because it is all homogeneous, actually because it's a homogeneous deformation, so whatever is happening at the boundary will also happen in the interior, because everything is homogeneous in this particular case here. So you will get that beta naught plus beta 1 times lambda 1 square plus beta 2 times lambda 1 raised to 4 is equal to 0, and beta naught plus beta 1 times lambda 2 square plus beta 2 times lambda 2 to the 4 is equal to 0, and beta naught plus beta 1 lambda 3 square plus beta 2 times lambda 3 to the 4 is equal to t bar. So the t bar is the traction. So this is the third direction, and the t bar is being applied in the third direction. The lateral surfaces are traction free, so you will get that this is equal to 0 here. Fine. Then now you can see that from these two equations, lambda 1 is equal to lambda 2 is one possible solution. That's one possible solution. See, we cannot assume that that is the only solution because of the non-linearness. So we have to be very careful here. So, but at least we can say it is one possible solution here from these two equations here. Okay. Then, so if we assume now that this, let us say that lambda 1 is equal to lambda 2, then let us see what solution we get now for this, for a Cylindrical. So now we will specialize this particular solution for a Cylindrical table. Look at that now. So for a Cylindrical material, material, you will get that beta naught is equal to 0, beta 1 is equal to lambda 1 square plus lambda 2 square plus lambda 3 square minus 3 times lambda minus 2 mu divided by lambda 2 times lambda 1, lambda 2, lambda 3, and beta 2 is equal to mu divided by lambda 1, lambda 2, lambda 3. So this is what you will get. Now you will get, so assuming that lambda 1 is equal to lambda 2, so lambda 1 is equal to lambda 2, then what you will get is that for h, which is lambda 1 square, you will get the equation that a times h cube plus b times h square plus c times h plus d is equal to 0. So this is the equation that you will get here for as a governing equation here. Okay, then you can solve for this particular equation. So this is a non-linear equation, and then you can find the roots of this particular equation here. Then what you will get, so you know, these coefficients are known. So a is equal to 2 times lambda plus mu, and then b is equal to t bar square lambda cube by kappa square mu square minus 7 lambda minus 6 mu, where this kappa bar, where this kappa is 3 lambda plus 2 mu. So this kappa is equal to 3 lambda plus 2 mu, and so this is b. Then c is equal to 8 lambda plus 6 mu, and d is equal to minus kappa. And so all these things are known, correct? Because we know what the material properties are, and now you can solve for these particular you can solve it for this h in this particular case here. So what you will get is the following. So this do not confuse between the lambda 1, lambda 2, lambda 3 and this lambda. This lambda is the Lame parameter, so the same as this lambda here, and so that is a known quantity here. So basically all these coefficients A, B, C and D are known because the t bar is known. So then you can solve for these things. So so let us solve one or two cases here. So for E is equal to 2.5, E is equal to 2.5, then mu is equal to 0.25, and T bar square is equal to 1. So that means T bar is equal to plus minus 1, let's say. Then we will get that there is only one solution. You will get that lambda 1 is equal to 0.928, and then lambda 3 is equal to 1.24625. So basically, you will see that for this t bar equal to plus 1, you get only the solution for extension, but there is no solution for compression. Okay, so that means, so as I said, that the Savina-Kirchhoff material model has problems, right, in compression. So this is one of the problems, that there is no solution for t bar equal to minus 1. Okay, so only for t bar equal to plus 1, you have this particular solution here. So no solution for t bar equal to minus 1. So this is, as I said, that this is a defect in the Savina-Kirchhoff material, that under compression it has a problem, that for large compressive values. So actually, if you compare, this is a very large load, I mean, as compared to the E value, correct? And so that is the reason that under very large compressive loads, the Savina-Kirchhoff material model fails to give a solution here. But if we now take t bar square equal to 0.16, so t bar square is equal to 0.16, so that means t bar is equal to plus minus 0.4, then actually we will get the following solutions for lambda 1, lambda 3. Okay, so we'll get three solutions now. So they are 0.966, then 1.13, then 1.06, then 0.68, and 1.08 and 0.516. Okay, so so the first solution here, this corresponds to t bar equal to 0.4, and these two solutions, they correspond to t bar equal to minus 0.4. So now you can see the non-uniqueness in the solution, right? So for a tensile load, you get only one solution, but for the compressive load, you get these two solutions here. So in actual practice, then you may ask that in actual practice, which of these two solutions is going to be realized, right? So you can think of it this way, that finally all problems will be transient problems in a practical sense, that you are increasing the load from 0 to this point node, right? And so the solution that occurs first, right, when you are compressing it gradually, whichever solution occurs first, that will be the solution that will be achieved, right? The other solution will not be achieved in practice, but theoretically it is possible to have the other solution also. So here in this particular case here, this solution will be achieved first, because this is your lambda 3 value, and that is larger. So if you start from 1, correct, and now you are compressing it, 0.68 will be reached before 0.516, and so this is the solution that will be achieved in practice if you start increasing the compressive load gradually from 0 and then increasing the load here. But this is a very nice example to show that to show the non-uniqueness of solutions, and also the pathology that exists in the Savina-Kirchhoff material model, in the sense that there may be no solution beyond a certain compressive load. There may be no solution here. So because here we took this t bar to be small, we got solutions. But if you increase it, in magnitude to -1, then you would not have a solution in the compression case. So, so this sort of gives an idea about the non-uniqueness of solutions here. Okay, now we will restrict ourselves. So, for the remaining solutions, we will restrict ourselves to incompressible materials. Okay, and so Rivlin was the first person to come up with very interesting solutions to the nonlinear equations of elasticity. So, very general solutions without assuming a particular model, constitutive model. He came up with some very general solutions, and so we are going to look at some of those solutions for incompressible materials now. Fine. Then first let us look at what is the constitutive relation for an incompressible material. So far we have not actually looked at incompressible elastic materials. So let us look at that. So the constitutive relation. So let me write that first. So incompressible, compressible material model. So the constitutive relation is given by minus p of x comma t times identity plus beta minus 1 of invariance of b. So this is actually, this will be just I1 and I2 in this particular case. I1, I2 times b inverse plus beta 1 I1, I2 times b. So here you can see that this part for an incompressible material model, this part is constitutively indeterminate. Constitutively indeterminate. So basically this part, so if I give you the left Cauchy-Greenstein tensor, you will not be able to determine this particular part here. Okay. So this particular pressure has to be determined from the boundary conditions, from the governing equation and boundary condition. We cannot determine it just if you give me B, we cannot determine this particular part here. So if you recall, even in your fluid mechanics also, when we assume an incompressible fluid, we have this constitutively indeterminate part. So this is exactly identical to that in the sense that that cannot be determined from the kinematical variable, and then you have to bring in your governing equations and the governing equation and boundary conditions in order to determine that particular part here, p of x comma t here. The remaining part is similar to that what we obtained by using the Rivlin-Eriksson theorem for a nonlinear solid here. So here only I1 and I2 enter because it's all deformations for an incompressible material are going to be isochoric, right, volume preserving, and so we will have that det f is equal to 1, right, det f equal to 1 for all deformation, all possible deformations of an incompressible material. So that means I3 will also be equal to 1 here. So so this is the constitutive relation that we are going to consider. I will prove that the constitutive relation has to be of this particular form when we do thermomechanics. So at this stage, let us not worry about how we got this particular form. So if you recall, for a compressible material model, you would have beta 0 of the invariance of B times identity, right? And then the other parts are the same. But in this particular case, this beta naught times identity is replaced by this pressure down here. So as I said, that the derivation of this particular equation, constitutive relation, I will do at a later stage when we do thermomechanics. But let us just assume this particular constitutive relation and then look at some of the solutions that we get here. Fine. So, okay, so let us look at the case where let's take a cylindrical coordinate system. So cylindrical coordinate system. Okay, so here let's see. So assume that, so we are going to look at a very particular or restricted class of solutions here. Okay, so where where it satisfies this particular assumption here, that tau plus p times identity is a function of R alone. Is a function of R alone. So that means this part, tau plus pi will be beta minus 1 times B inverse plus beta 1 times B. Okay, so that is the part. So that part is a function of R alone. That's what we are assuming. And then also assume that tau R theta is equal to tau R Z is equal to 0. And so these are the set of assumptions so basically we are looking at only very restricted class of solutions here. So the loading is such that these assumptions are satisfied here. Okay. So the del dot tau equal to 0, reduces to del tau R by del R plus 1 by R times tau R minus tau theta theta is equal to 0. Then del P by del theta is equal to 0, and del P by del Z is equal to 0. Okay, so this will imply actually that P is also a function of R alone, right? And so we have assumed that tau plus pi is a function of R alone, and now we have deduced that P is also a function of R alone, so tau is also a function of R alone. Right? So tau is also only a function of R. So that means it is not a function of theta and Z from this particular thing here. Okay. So so now let us look at what we get from this one. So from this particular relation, we will get that tau R is equal to integral of tau theta theta minus tau R by R times dr. Okay. And also from this particular relation, you will also get that tau theta theta is equal to d by dr of R times tau R. I need not use partial derivatives now because we know that it's only a function of R. So I can replace partial derivatives by total derivatives in this particular case. Okay, so now let us look at a particular problem here. So this is an annular wedge that is subjected to some loading here. So yes, so let us look at the annular wedge, which I will just draw. This is an annular Okay, so this symbol here stands for the load that is normal. Okay, so this N is a load that is normal to the plane. So that is why this cross circle stands for normal. So whatever loads that I am indicating here, this N or this T or this M and this R, these are resultants due to the tractions that are active on these particular surfaces. So for example, this R is the total load in the theta direction due to the tractions that are acting on this surface. Similarly, this moment M is the moment that is generated by the tractions that are acting on this particular surface, and so on. So this T is the torque that is generated by the tractions acting on this particular surface. This N is the normal force that is generated, that is the resultant due to the tractions that are acting on this particular surface here. Alright, so we'll use this now, these equations, whatever I have written here, in order to deduce certain features of the solution here. Okay, so the resultant load R now is equal to integral from R1 to R2 of tau theta theta times dr. Okay. So this is assume unit depth. Okay, so into the board you assume the unit depth. Okay, unit depth into the board. So this is into the board. So you will get this particular expression here. Fine. Then let's see. So this you can write as equal to R times tau RR from R1 to R2. So that is because we had seen that tau theta theta is d by dr. So since tau theta theta is d by dr of R times tau RR. So I'm just substituting it in this particular case here. Okay, so so if you now superpose a uniform pressure at R equal to R1 so as to make it traction free. Okay, so if uniform pressure is superimposed on R equal to R1 so as to make it traction free, is to make a traction free, then you will get that R equal to 0 if and only if tau RR at R equal to R2 is equal to 0. Because now the tau RR is the traction, right, in this particular case. So there is no tau R theta because all those things we have assumed to be 0, and then tau RR evaluated at R2 minus R tau RR evaluated at R equal to R1. But tau RR at R equal to R1 is 0. And so this will be equal to tau RR and R equal to 2 will also be equal to 0 if R is equal to 0. Then the resultant torque that is acting on this surface, that is T, is equal to 2 times theta naught times integral of R1 to R2 of R square times tau theta z times dr. So this is, all of this is obtained using x cross t. Okay, so that is the x cross t ds over s. So from that you will get this particular expression here. So there is an integral over theta also, because r dr d theta will be the area element. But since things are uniform, right, with respect to theta, the 2 theta naught will come out. The theta naught is this included angle. So that will come out of the integral here. And so basically the integral with respect to theta will give that 2 theta naught. And let's see, so this this is the expression for the torque. Then let us look at the expression for the bending moment here, m. So that m is equal to now integral of r times tau theta theta times dr from R1 to R2. And you can do a series of manipulations. So I will not go over those manipulations, but I will just mention it. So this can be written as integral of R1 to R2 of r times tau theta theta plus tau RR times dr plus half of integral R1 to R2 times r times tau theta theta minus tau RR times dr. And then what you will get, so after a series of manipulations which are given in the book, you will finally get that this is equal to half of r square times tau r from r1 to r2 plus half of integral of r times tau theta theta minus tau r times dr from r1 to r2. Okay, so now you may ask that why don't we just evaluate this integral directly? You know, what is the purpose behind carrying out all these manipulations? Why not just evaluate here? I mean, why do you need to do these series of manipulations and get it to this particular form? So the motivation there is that see, he was trying to solve Rivlin, so who did this first, he was trying to solve this problem for any arbitrary constitutive relation. So let us go back to this constitutive relation here. So this is tau is minus p of x comma t times identity plus beta minus 1 of I1 I2 times b plus beta 1 I1 comma I2 times b. Correct? So this is the constitutive relation. Now you will see that if I can get an expression for the difference of the two normal stress components, then that will not involve this p, correct? Because that will get cancelled, right? So for example, tau r minus tau theta theta will not involve p, correct? Will not involve p, because that will get cancelled, right, from the two expressions here. So if I try to evaluate this directly, then I need to know what that pressure is, okay, and that is constitutively indeterminate. So I cannot find that p unless I know b, correct? Unless even if I know b, I cannot find that p, and so I would not be able to find this. Even if I knew b, I would not be able to evaluate this. So the purpose behind carrying out all these set of manipulations was to get differences in the normal stress which would not involve the p part in that. And so as I said, that you need not try to memorize these manipulations. Okay, so if you are given a particular problem in your assignment or test, you can sort of just proceed from first principles and try to solve the problem. You are not expected to know these derivations. As I said, that these manipulations have been carried out in order to keep the constitutive relation very, very general. Okay, so that this constitutive relation. But I mean, your assignment problems or your test problems, they will involve a particular constitutive relation. So we are not going to try and find the solutions for very general constitutive relations. So to summarize, if you are given a similar problem where you are asked to solve for the response of for some geometry, then just proceed from first principles. Do not try to do any of these manipulations that have been shown on this board here. Okay, so that is one thing that I would like to mention here. Then similarly, let us find an expression for n. So again, see, the whole purpose is again to do these manipulations and get everything in terms of differences in the stress components here. So let us now look at n also. So n will be equal to 2 times theta naught times integral of tau zz times r times dr from r1 to r2. Okay, and so again, after a series of manipulations here, what you will get is that you will get theta naught times r square times tau r times r1 to r2 plus integral of r1 to r2 of 2 times tau zz minus tau r minus tau theta theta times r times dr. So again, you will see that basically the manipulations are done such that the pressure part will get cancelled, right? So the tau zz will involve a minus 2p, and then this will be minus of minus, so this will be plus p, and then again this will be minus of minus, so this will be plus p, and so the pressure part will get cancelled here. So the whole goal behind doing these manipulations is to not worry about the pressure part, because that is, as I said, that is a problematic thing, because that is constitutively indeterminate, and so somehow we are trying to eliminate that. But as I said that his goal was to do it for arbitrary constitutive relations. But if you give me a particular constitutive relation, then we need not carry out these manipulations. We can directly evaluate these integrals by first finding the pressure and then substituting that pressure into the constitutive relation and then integrating this constitutive relation. So I will repeat that in your assignments and tests, you need not do these manipulations. So just try to solve it from first principles as I already indicated here. Okay, so this sort of brings us to the end of this particular class. So what we have done is that for this particular annular bridge geometry, we have found out the expressions for the resultant force R, the bending moment M, the torque T, and the normal force N. And then in the next class, we will now look at actual solutions for particular problems such as bending and stretching of a rectangular rod or the torsion. So all these will be now nonlinear solutions in the sense that for the constitutive relation that I had indicated with the pressure part, and so we will look at those solutions in the next class.